In this video, we're going to wrap up our discussion of linear motion by talking about free fall. Okay, so an object in free fall is going to be basically just under the influence of Earth's gravity. So as soon as I let this water bottle go, it's undergoing free fall. You guys couldn't see that very well. I need to move it over here. Yeah, free fall. That's an example. Okay, you can do it at your house too. Drop something, that's free fall. Actually, as soon as I let go and I throw this up, okay, that's also free fall, regardless of its direction of its velocity. As long as it's only experiencing gravity, then the object is in free fall. Regardless of how you throw an object here on Earth, it's going to end up going back down to the ground, and that's because Earth has a gravitational field and pulls things down towards the center of the Earth. So objects are accelerated due to Earth's gravitational field. And the magnitude of that acceleration is, on average, about 9.8 meters per second squared. And that's the value we're going to be using in this class for the acceleration due to gravity. But it's interesting to note that gravity is slightly different, or the acceleration due to gravity is slightly different because Earth's gravity varies depending on how close you are to the center of the Earth. So with increased elevation, the value for g would be slightly less, or at the poles, because the Earth is kind of squished a little bit, and the equator's a little bit thicker than the pole. At the poles, basically, you're a little bit closer to the center of the Earth. So the gravity in the Arctic is going to be, the acceleration due to gravity is slightly larger there. So that's kind of interesting to note. We will use 9.8 meters per second squared for g in all our problems. But that is kind of an average value, and it varies slightly from place to place. So again, as a reminder, in the Arctic, you could have an acceleration due to gravity of 9.834-ish, and then there's mountains in Peru where it's 9.76. So it does vary slightly. So gravity acts downward towards the surface of the Earth, regardless of the velocity of the object. Okay, so here in my reference frame, I've set the vertically upward direction to be positive, and here let's say this ball has a positive velocity. Okay, well, its acceleration is going to be negative then, okay, because acceleration is always going to point downward in this reference, or downward towards the surface of the Earth, and in this reference frame that's negative. So our value for the acceleration in the y direction is going to be negative g, or negative 9.8. Meters per second squared. Okay, an example of this, tennis server throws the tennis ball up. Okay, in its upward motion, the tennis ball has a positive velocity, but its acceleration is negative. Right, it goes up and it's going to be slowing down because its acceleration is in the opposite direction of its velocity. Okay, when objects reach the peak, you throw that tennis ball up, it's going to come to a point where it stops for a second, and then it's going to start falling back down. So even if the velocity is 0, that acceleration is still negative 9.8 meters per second squared. Okay. Example of this, if you jumped into a pool or something for a split second, you might feel like you're not going anywhere, you stopped in the air. Okay, that's also an example of where you've reached that peak height. Your velocity slowed and slowed and slowed until it was 0 for a split second, and then you start falling again because your acceleration throughout the whole time that you're in the air is negative 9.8 meters per second squared. And again, if you have a negative velocity, or if an object has a negative velocity in this reference frame that you've set up, acceleration is still going to be negative g. Okay, so an example of this is when divers dive off the platform. Okay, they're falling towards the pool. They have a negative velocity in this reference frame that we've set up, and their acceleration is still negative g. So in this case, they'd be speeding up because their velocity and acceleration are in the same direction. Okay. So this slide was basically just to show you that regardless of what the velocity is, if the velocity is positive, negative, it's for a split second 0, if an object is in free fall, then its acceleration is going to be negative 9.8 meters per second squared. Okay, we can also experimentally show this. So let's say that we dropped a basketball, maybe in the gym from the second story over. It's been a while since you've been at the school, but let's say over the railing, we just dropped a basketball. Okay, and we had a high-speed camera, and we were able to, every 0.1 second, figure out what the y position was from the starting position of 0. Okay. Well, if we graph that position versus time, and in this case, instead of an x for position, I'm using a y for position. Okay. If we graph that over time and fit a best fit line to it in Google Sheets or in Excel, okay, we would notice that a parabola, a 2-degree polynomial, works really well. Okay, and take a look at what's going on right here, this negative 4.9. Okay, that's negative 1/2 times 9.8, right? So that's showing that here we've experimentally confirmed that the object has a constant acceleration, negative 9.8 meters per second squared. So that value for g that we would find if we set negative 1/2 g equal to negative 4.9, we would get 9.8 for g. Okay, so you can experimentally determine that value too. So if we were to make a graph of an object in free fall of velocity versus time, okay, specifically for this basketball that we're dropping, and again, we're just looking right now at this just first 1 second. So we've kind of taken a lot of data points for just this first second. Your slope would be negative 9.0 meter, or negative 9.8 meters per second squared. Okay, because your slope is rise over run, and your rise would be in meters per second, and your run is in seconds, so meters per second squared. Okay, and we found from fitting the parabola to our data previously that that acceleration was negative 9.8, and we know that the slope of our v versus t graph is our acceleration. Okay, and then if we were to make an acceleration versus time graph, not super exciting. You have a straight line, straight horizontal line at negative 9.8 meters per second squared. Okay, so experimentally it's been determined, and this is for objects that have a relatively low velocity, basically so air resistance isn't a factor. Okay, so some objects even at low velocity might have a high air resistance, so those would be exceptions to this. In general, low velocity and low air resistance is the important thing, and you'll see a constant acceleration towards our surface of 9.8 meters per second squared. Okay, great news. The 4 equations that you learned for horizontal constant acceleration motion are still in play. They still work. We're going to make some small adjustments to our variables just to indicate that we're dealing in the y direction instead of the x direction, so the vertical direction instead of the horizontal direction. And it's good practice to get in like just to write down if it's in the x or y, so to write these subscripts because in the future we'll be doing projectile motion or like 2-dimensional motion where you're dealing with both, and you got to keep your variables straight and keep your numbers straight. So it's good practice to, even if we're just dealing in the y direction, to write those y's. Okay. The one other thing you'll notice about this is I've replaced all the a's with a g. Okay. Now you want to be careful here because g in a lot of cases is going to be negative. Okay, so this sign right here could be minus gt, depending on how you set up your reference frame. So g is always going to point towards the surface of the Earth. So depending on how you set up your reference frame, you might have to put a negative 9.8 meters per second squared in here for g. Okay, how I usually solve these problems, I like to write the negative sign and call the positive direction upwards. For some of you, it might be more comfortable to call the positive direction downwards, and that way you don't have to worry about making g negative. Okay, but then you don't want to confuse your velocities. You've got to be consistent with everything, with your velocities, with your positions, and with your acceleration or your gravity in this acceleration due to gravity in this case. Be consistent with which direction you're calling positive, which direction you're calling negative. Okay, so that's what I say over here. Use the correct sign for g. If you've chosen up to be the positive y direction, you have to use negative 9.8 for g. And if you have chosen downward to be the positive direction, then you're going to need to use a positive 9.8 meters per second squared. So thanks for watching. Make sure to watch the next video with some examples of using the big 4 kinematic equations for free fall.